get going. Okay, so we can start now. Good evening, friends. Very happy to have Subir Sarkar with us. I mean, I know him since, I don't know, 40 years perhaps now, because Subir was born and educated in India and he obtained his PhD in 1982 from the Tata Institute of Fundamental Research, the same place where I got my PhD from, and we had some overlap. And then later, since 1990, Subir has been at the Rudolf Pyle Center for Theoretical Physics in Oxford. He served as the head of the particle theory group during 2011 to 19, and now is Professor Emeritus in Physics and Emeritus Fellow of Linacre College, Oxford. Subir has very wide-ranging research interests at the interface of fundamental physics with astrophysics and cosmology. This covers topics such as Big Bang nucleosynthesis, dark matter, dark energy, inflation, cosmic microwave background, relic topological defects, weak interactions, neutrinos. Subir also works on high energy cosmic rays, gamma rays, and neutrinos, and belongs to the IceCube Neutrino Observatory and the Cherenkov Telescope Array collaborations. Previously, he worked on the Pierre Auger Observatory for Cosmic Rays and the CERN BEBC Beam Dump Neutrino Experiment. Subir also participates in laboratory experiments using high-powered lasers to investigate astrophysical processes and programs on quantum sensors for fundamental physics, as well as the legacy survey of space and time on the Vera Rubin Observatory. So today we are going to hear from Subir about challenges for the standard model of cosmology. It's a pleasure having you with us, Subir. Over to you.
Thanks a lot. I must say it is a luxury to be able to give a talk where there is so much time for discussion afterwards. But I will say at the outset that people are free to interrupt me if they are puzzled by anything that I say, rather than waiting for the whole hour for me to finish. So, my topic today is the standard cosmological model, and that's depicted here in the form of a computer simulation, Hubble volume, which studies the formation of structure in a universe dominated by a cosmological constant and whose major matter component is cold and dark. And the net result from such simulations, this is the zero redshift snapshot, does look pretty much like our real universe. And what I want to emphasize here is that this picture, although it looks quite complex and has this grand so-called web of cosmic web of structure, this tracery of galaxies, clusters, superclusters, and so on, it is in fact still, statistically speaking, it is isotropic and homogeneous. That's because the underlying assumptions of the model, which is being simulated here, is that the underlying metric of space-time and the fluid that fills this universe, they are isotropic and homogeneous. Now, today I'm going to talk about some observational results that challenge this cosmological principle on which this model is based. And I know that most of this audience are interested in fundamental issues, but I want to start with a caveat that my philosophy in this study is something that I learned from Dennis Sharma, who I was privileged to work with when I first came to Oxford. And he introduced me to cosmology. And he wrote in a book a few years before I met him that the real questions about the universe are, of course, the profound ones that we all worry about: why anything should exist, why there is a universe at all. But the first thing to do, to paraphrase him, is to start by describing the universe as it actually is. And what I will present in this talk is our own attempts to find out what the universe actually is like, rather than trust to grand principles like the cosmological principle. Now, the reason why we need a principle at all in cosmology, as you all know, we are rather restricted in what we can learn about the universe. It is just what comes to us along our past light cone and within it. And this has been emphasized by George Ellis and others as something that perhaps distinguishes cosmology from other sciences where we have the luxury of repeatable measurement and so forth. So we have to necessarily make an assumption that our position is not special, if you like, an extension of the Copernican idea. Now, a small caveat here. In principle, one could try and determine what an observer across the Hubble volume sees by looking at certain subtle effects. For example, the kinetic Sunaev-Zeldovich effect in clusters, in principle, can afford us a view of the universe from a different vantage point. In practice, it is today impracticable. So we'll stick to this point here. Now, this cosmological principle was, of course, implicit in the work of Alexander Friedmann and Lemaitre and so on, going back 100 years. But it was, to my knowledge, first formulated as a principle by Edward Milne, who was here. In fact, he was the chair of mathematics, Rogers' predecessor at Wadham College. And he basically said something that no one can disagree with, very sensible idea. Universe must appear the same to all observers. Now, by the time this idea traveled to Cambridge, they wanted to go one better. So they said Milne's principle is too restricted. Why do you want it only to be not special in space? It should also be not special in time. And thereby Bondi and Gould formulated the perfect cosmological principle, which led, as you know, to the steady-state theory of the universe. And that was philosophically perhaps an even better model, but it was sadly falsified by observation, the discovery of the cosmic microwave background. Although, to be fair, it took until 1992, when Kobe measured the spectrum of this background to be very accurately a black body, and thereby ruled out alternative ways of creating that spectrum, that we could definitively accept that the universe had a hot, dense past. There's no way it is steady state. However, the spatial part of the cosmological principle was not abundant, although the time part was. And the reason for that is very obvious. As Weinberg says in his text from which I learned cosmology, the real reason why we adhere to the cosmological principle is simply because it's the most optimal thing to do when you have limited data. You start with the simplest possibility. But he did say, if the data will not fit into this framework, we shall be able to conclude that either the cosmological principle or the principle of equivalence is wrong. Nothing could be more interesting. And this is the bit that I find somewhat surprising, that people have not taken notice of this as much as they ought to have in the last 50 years. So back to this picture of the simulation of today's standard model of cosmology. As you know, we base it on the assumption of a maximally symmetric spacetime, the Friedmann, Lemaitre, Robertson, Walker metric, which I have written here suggestively like a Minkowski metric by using conformal time rather than real time and avoiding all the angular part. Of course, because the scale factor would then appear below dt squared, eta is a dangerous quantity to play with, but it makes you clear that this metric is conformal to a Minkowski metric. And then we have from this we can construct the various quantities that go into Einstein's equations. And on the right-hand side, we have the energy momentum tensor, which was initially taken to be that of non-relativistic particles, dust. But in the 1930s, when we realized that particles are excitations of fields, it was also recognized by Zeldovich, Pauli, and so on, that the fields would contribute to the energy momentum tensor, a component with negative pressure. So the cosmological constant in the equation would not just be the geometrical part on the left-hand side, which comes from the underlying covariance, but also the contribution from the fields. And it is the two that add up together to enter the Friedmann equation, Friedman-Lemaitre equation that results from the vast oversimplification of the setup due to this assumption of maximally symmetric space-time and ideal fluid. So this lambda, innocuous lambda here, is the sum of two components which don't know anything about each other, and yet they must add up to give you something of order h naught square, because if I take this equation and divide it through by h naught square, I get this famous sum rule for the fractional components of the energy density in matter, in curvature, and in lambda. And this, of course, is the definition of the model. That's why they add up to 1. This sum rule is simply saying we are not allowing any complexity into the model. There's no vorticity or viscosity or angular momentum or back reaction or whatever. Now, when we supplement the Friedman-Lemaitre equation with the simplified form of the Raychaudhuri equation, which tells us how the scale factor acceleration reacts to the pressure and the energy density, rho plus 3p is the total gravitating part, since the pressure also, of course, is kinetic energy, it gravitates. And that has allowed us to use this equation and this sum rule to interpret the data that did come subsequently in the last 20 to 30 years from a range of observations covering the Hubble diagram of standard candles like type 1 supernovae, shown here, from looking at standard rods like the angular scale of fluctuations in the microwave background, which peak at about a degree or a multiple of around 200, as you see here, or the same fluctuations in the radiation, which was coupled to the matter initially, are reflected in the so-called baryon acoustic oscillations in the power spectrum of galaxy clustering. And this has recently been mapped exquisitely by the dark energy spectroscopic instrument, or DAISY. So if you put it all together in this simple 3-parameter model, then you find that because the curvature is set to be close to 0 by the position of this first peak, which goes as the square root of the curvature, then you have only 2 parameters. And in that 2-parameter space, the supernovae impose a diagonal constraint as so. Omega matter minus omega lambda is some small negative number. And then you have the other diagonal at right angles is the one from the microwave background that says those two things add up to 1. And then you put in the constraint from clusters of galaxies, from baryon acoustic oscillations, and they pick out this combination of omega lambda being 0.7 and omega matter being 0.3. Notice that we actually deduce lambda from the sum rule here, and that because omega lambda is lambda over 3 h naught square, this means that lambda is of order 2 times h naught square. So this quantity, which is, as I emphasized, a balance between an arbitrary geometrical quantity lambda, little lambda, and a contribution from quantum fields, somehow has to have a value of order the present Hubble expansion rate. So I want to pause a moment to emphasize this. This is neither fundamental nor a constant, and yet it is imprinted on this quantity lambda by the very structure of the model in which we are interpreting the data. I would go far further and say the oversimplified model in which you are interpreting the data. So the physical scales here, as a particle physicist, I always think about where the scales come from. So the fundamental scale is, of course, Newton's constant. That's in particle units is the Planck scale. And the other scale is an infrared scale. That's the size of the universe, 10 to the 28 centimeters. In energy units, that's 10 to the minus 42 GeV. So we are now playing with 2 energy scales, which are different by about 60 orders of magnitude, and they both enter into this, forced to enter into it by the structure of this model. So to cut a long story short, for the past 20 or 30 years, we have been pursuing this model and measuring the parameters with increasing so-called precision. And we have pictures like this showing what the universe is supposed to be made of. The most important ingredient in terms of the fraction it occupies is this lambda, or more generally dark energy. And if you express that lambda in terms of energy density, then I have to write it out in Planck units. So it's h naught squared divided by 8 pi g, or if you like, multiplied by Planck mass square. And that then is the geometric mean of the Hubble scale and the Planck scale, which is 10 to the minus 12 GeV, or the present day microwave background temperature. Not a coincidence. That is the way we constructed this. And then people, of course, worry about where this scale came from, and why is it of the same order as the matter today, etc., etc. But the fact is that this has no physical foundation. It has got nothing to do with microphysics, in particular, the standard model of the fundamental interactions. So, although we have invested a huge amount of effort in pursuing this precision cosmology through beautiful instruments and beautiful data, somehow the foundational assumptions of the standard cosmological model, which have led us to this situation, they have not received as much attention. I should say my collaborator Nathan Seacrest, who is an astronomer, emphasized to me the difference between precision cosmology and accurate cosmology. He said, well, this is precision cosmology. Accurate cosmology is akin to, if you recall, when the Hubble Space Telescope was launched, its mirror turned out to be flawed. It was, in fact, precisely ground, but to the wrong shape. So that's the difference. Okay, we want to find out what's the right shape of the universe. A very quick aside, because a lot of people think this, and I just want to assure them that they think that the cosmic microwave background has established that there is a cosmological constant. So here is the cosmological, the power spectrum of the CMB fluctuations. Indeed, it is very well fitted by this 6-parameter lambda CDM model. And here is the table from the Planck paper telling you what all those parameters are: the baryon density, the cold dark matter density, the optical depth to last scattering, the amplitude of the perturbations, spectral index, etc., etc. I invite you to find here where the entry for lambda is. There is no entry for lambda because it is not actually something that determines those fluctuations. You infer it from that sum rule that I mentioned. Omega k comes from the position of this peak. Omega matter is derived from the ratios of these peaks. And omega lambda is obtained from this equation by subtracting them from 1. In principle, you can look for lambda in correlations of the microwave background with the large scale structure. That's the late integrated Sachs-Wolf effect, but it's a very tiny effect. You would expect it to be of order about 1 microkelvin. And indeed, attempts to see it have so far not been therefore successful, because you really need about 10 million galaxy redshifts over the range 0 to 1 to see this at 5 sigma. That data is now almost here. DAISY has collected that order of galaxies in spectroscopic redshifts, so we should soon know the answer.
So wait, one quick question.
Yes.
If you did not assume the sum rule of 1,
yes,
how would you go about fitting the data? Say you don't care about that 1.
That it does not enter into fitting any of this. Okay. The flatness here, this omega k is set by this peak here. It's actually got a slight degeneracy with other quantities, but to first order, it just goes as square root of omega k. So, for example, if you had large curvature, that could do the same job as lambda.
So we can have a omega total much less than 1, or say around omega 0.3 universe?
In principle, the CMB actually indicates a slightly open universe from other things, from lensing, which I won't go into here. But my point is that you assume that sum rule, but nobody has told you that there are only 3 terms in that sum rule.
Yes, okay,
right?
agree.
That
yes.
is that assumption of isotropy and homogeneity, which I alluded to earlier.
Okay, thank you.
So a very quick word, since one has to emphasize how big this problem is. And I must say, I'm constantly astonished that people have accepted the standard cosmological model when they are aware that we have a perfectly good quantum field theory of the fundamental interactions that works very well up to some scale of order a TeV, to which we have tested it in the laboratory. And as you know, we have now found the missing piece. We are in the process of trying to determine the potential of the Higgs. Particle theorists also know, because they have been doing this for the last 30 years, that you could parameterize physics beyond the standard model, which must exist to explain the observed facts of the universe, by invoking operators which are not renormalizable operators, but which violate some of the symmetries of the standard model. For example, lepton number or baryon number or so on. What is more interesting for cosmology are two terms which are in fact of dimension less than 4. And these we call super-renormalizable terms. One is this term here, m squared phi squared, which is what has occupied particle theories, because this is the notorious divergence of the mass of the Higgs if it is a fundamental particle. If it is fundamental, as it goes in the vacuum, it sees everything else and it couples to them, and it thereby gets a correction to its own mass. And that mass diverges as the square of the energy scale up to which we do the integration. In other words, the lower we go in energy in distance scale, the higher this mass goes up. Now, you might wonder why that doesn't happen for other particles that we think are also fundamental, like the electron. That's because the electron has a chiral symmetry. It has got a handedness. And in fact, if the mass goes to 0, then that handedness is absolute. You can't race ahead of the electron and see it spinning in the opposite direction. And therefore, that chiral symmetry, we say, protects its mass. It gives you an understanding of why that mass should be small. But the Higgs is a scalar particle. So the only way to protect it is to either make it composite. For example, the pion is a scalar particle, but it is composite. We have no problems with the pion mass. Or the other option is to say that the Higgs is connected with another particle, which is its fermionic partner. We call it the Higgsino in the scheme called supersymmetry. And the mass of the Higgsino is protected by chiral symmetry. Therefore, the Higgs is protected. Anyway, that's a whole different story, which you won't go into today. Today's concern is that first term, which is the vacuum energy of the electric theory. Now, strictly speaking, you can't calculate vacuum energy in a quantum field theory. You can only calculate the differences in it, not the absolute value. But we know that the scale of it should be set by the only scale in this theory, which is the TeV scale, the scale which is determined, say, from muon decay, from a perfectly experimental observation. Now, this, as you can see, is already 60 orders of magnitude higher than the energy density that we calculated in the last slide. And therefore, if it actually gravitated, then it is easy to show that the universe should not have survived past the electric scale. In other words, about 10 to the minus 12 seconds after the Big Bang, it should either have recollapsed or gone into exponential expansion forever. I mean, depending on the sign of lambda, which is also something not calculable in field theory. Now, this was, of course, observed by Pauli way back. And he said that, it can't be. This, from experience, this 0-point energy does not couple to gravity. But he didn't say why it should not couple to gravity. According to Einstein, all energy density couples to gravity. And to date, we don't know the answer to this question. However, people have worried about the second problem raised by having a finite vacuum energy density. Why is it of the same order as the matter density today? Because the matter density is going as z cube, and this one is not changing. So you could try to make this lambda a dynamical quantity by making it the energy of some scalar field, which then would have a tracking behavior. There'd be some infrared fixed point so that it has the same value as the matter density when you solve the coupled equations. But to construct such a scalar field is very non-trivial, because its height has to be of order the vacuum energy that we want today. But in order for this scalar field to feel the Hubble expansion, its mass should be of order the Hubble parameter. So its mass has to be 30 orders of magnitude smaller. So when you look at it carefully, it's exactly as much fine tuning as the bare cosmological constant that we abhor, right? So all these quintessence models don't solve anything. They don't even solve the original cosmological constant problem, and they introduce a new one. And the same problem applies to attempts to modify gravity on some particular scale. It's a neat idea that gravity propagates in more dimensions than the ones we live in. But that scale, the only scale in gravity, is the Planck scale. So, in order to make it cosmologically relevant, you have to make this scale instead the Hubble scale, which is different by, as I said, 60 orders of magnitude. In fact, 120 orders of magnitude. So, to cut a long story short, every proposal to explain dark energy, okay, a recent example is massive gravity. Guess what mass the graviton has to have in order for this to be relevant to cosmology? You have to give it the mass has to be of order the Hubble parameter, 10 to the minus 42 GeV. So uh, people have expended a lot of effort in trying to explain dark energy, and lots of interesting things have come out of those studies, but none of them have addressed the cosmological constant problem. And in fact, uh, a trivial explanation would be if lambda is always of order h square rather than h sub 0 square, but that can be dismissed right away, because then you see you can just take lambda to the left hand side, and that corresponds to a renormalization of Newton's constant, which is ruled out both phenomenologically and also because it doesn't address this issue. So my own interest in this problem comes from the fact that H naught is the only scale in the Friedmann-Robertson-Walker model apart from the Planck scale. And this enters in every cosmological observation you make. So is its value imprinted on lambda by construction, by interpreting data in this model? Interestingly, recent work by string theorists has found that something that actually was already noticed back in 1982, I recall, 83, when the first string or the second string revolution happened. That if you had a de Sitter background, then there is no future infinity, and you can't actually impose unitarity of the scattering matrix, which is the most fundamental thing that you have in particle physics. Two particles scattering and going off to infinity. You can't conserve the probability. And there is a speculation that any S matrix formulation of quantum gravity will exclude de Sitter. Nature should avoid de Sitter for that reason. But that's not today's topic. I'll talk today about data. So we have indeed a very successful cosmological model as far as the growth of structure in the universe is concerned. I already talked about that earlier. And the idea is that some tiny fluctuations created by some mysterious process in the early universe called inflation, which we can see the imprints of in the cosmic microwave background, has then grown under gravity and gravity alone to create this cosmic web today. All you need for this to happen is about 6 times as much matter that does not interact with radiation as baryonic matter. Otherwise, there is not enough time for the structure to grow by the present day, right? So there is this dark matter component to this. However, on the whole, this is a pretty model because it does engage with a huge body of observations, and by and large satisfies most of them, right? However, this ends in our accepting that the real universe is inhomogeneous as we see it around today. So how well does it conform to this model description in the Friedmann-Lemaitre-Robertson-Walker? Now, on the left here is a picture of our local universe as mapped by the Cosmic Flows 3 survey, led by Brent Tully and company for many decades. We are at the center of this picture, and we are moving towards this thing that you see here marked Shapley. That's a supercluster of galaxies. These fine lines that you see here are velocities, and there might be actually a void over here that is even pushing us in this direction, but certainly Shapley is attracting us. Now, remember, this is only the visible matter. We don't see the dark matter. The dark matter distribution is, however, expected to be more or less traced by the visible matter on these large scales, which here is of order about 250 megaparsecs. If you go even further, you have mapped out things to 600 megaparsecs, now a little bit deeper with the DAISY survey. And again, you see this cosmic web. But again, what you're seeing is just the baryonic matter, the visible matter. The bias between that and dark matter is supposed to be of order 1 on these scales. The point I want to raise is, if you look at this picture, the questions arise, can we really approximate this as homogeneous? Can we assume that we are typical observers? Does it not matter whether we are in a void or in a dense region? Gravity is a local phenomenon. Can we assume that all directions are equivalent? Does it not matter if I look through the holes in the matter distribution or along a filament? Now, the basic story currently is that we adopt this FLRW description and we say that there are perturbations on top of it, which we call peculiar velocities, which is just the difference between a velocity as it should be according to distance, according to the Hubble flow. But there is a discrepancy, which is of order a few hundred kilometers per second. And this is attributed to local inhomogeneities. So, for example, Andromeda is falling towards us. It's not going away from us in the Hubble flow. And we are going towards the great attractor. But if that is the case, then our velocity should fall off as 1 over r. And then we should converge by Shapley or so to this frame, the so-called cosmic rest frame, in which the universe is actually isotropic and homogeneous. Does this actually happen? Now, the fact that we have a peculiar velocity was already known in the 60s, and Dennis Sharma, who I mentioned earlier, actually predicted in a paper in 1966, which I'm sorry to say has only 14 citations to date in Physical Review Letters, and this is a later one in Nature with Stewart. They predicted that the cosmic microwave background, which had just been discovered, should not be isotropic. It should have a dipole anisotropy, because we are not in the cosmic rest frame, because we are being pulled by local inhomogeneity and have a so-called peculiar velocity with respect to the Hubble flow. So soon afterwards, various people, including George Smoot, detected this dipole anisotropy, and Jim Peebles and Dave Wilkinson calculated in special relativity that this should be the effect of aberration and Doppler shift. Today, we set it as a problem in special relativity classes. And since this anisotropy is of order 1 part in 1,000, so is our velocity with respect to the speed of light. So it's about 370 kilometers per second. But in fact, our motion is rather more complicated, because not only are we moving around the galaxy, first of all, we are moving around the sun, but the sun is moving around the center of the galaxy, and actually it is moving in the opposite direction to this hotspot. So the two velocities add up, and our net motion, therefore, is more like 620 kilometers per second. And this net motion is the motion of the so-called local group, which includes the Magellanic Clouds, Andromeda, etc. We are coherently moving at 620 kilometers per second towards what was called the Great Attractor. I mentioned earlier the Shapley supercluster, which was one of the candidates for the Great Attractor. Now, if this story is true, then we should converge to the microwave background frame by averaging on scales larger than the scale at which the universe is supposed to become homogeneous, which is of order 100 megaparsecs. So I'll give you a spoiler alert right now. All observational data, for example, data on supernovae, is already corrected by first transforming to the CMB frame in which this isotropy and homogeneity holds. All the redshifts are boosted, the magnitudes of the supernovae are corrected, right? On the assumption that there is this frame in which the universe actually looks isotropic and homogeneous, although it certainly doesn't look like that from our vantage point. Now, with regard to the peculiar velocity, as I said, it should fall off as 1 over r, roughly, as we average over larger and larger scales, which is what is shown here in the denominator on the x-axis. This is the size of the box over which you are doing the averaging, and this is the bulk flow. And what you see here is the data until 2021, which was consistent with the purple line, which is the expectation of the standard cosmological model of lambda CDM. albeit a bit disturbing because most of the points are above it. There are none below it, but they're consistent within whatever this is showing 1 and 2 sigma bands. C11 was a measurement that we made, Colin et al. 2011, using the Union 2 catalog of supernovae, and that was discrepant, but only at about 2 sigma, as you see. However, subsequently, the Sloan Digital Sky Survey made a measurement which was somewhat more discrepant. They reduced their error bars. And most recently, the Cosmic Flows 4 survey has made two measurements of the bulk flow at distances of order 200 over little h megaparsecs, which are clearly discrepant. You might ask, how discrepant are these? Well, the statement made in their paper, which came out last year, is that this bulk flow has a probability of only 1.5 10 to the minus 4% chance of occurring, which is something like 4.6 or 4.7 sigma. Right? Clearly, there is a problem here. There is something rotten in the state of etc. Now, let me change tack, because if you show this plot to astronomers, they'll tell you, look, all these objects that are depicted here, their distances have to be estimated by means other than the redshift, because after all, they have a peculiar velocity. This is not just their Hubble expansion. So you have to have an independent estimate of the distance, and that is the hardest thing to come by in astronomy, in cosmology. And so you have to use various empirical methods, like there is the Tully-Fisher method for spiral galaxies. There is something called the fundamental plane relationship for elliptical galaxies. There are, of course, type 1 supernovae. But all these methods have uncertainties, and the systematic uncertainties for most of these measurements that are used here is as much as 15, maybe even 20%. So we can't really trust these things. That's what they will tell you. So let's turn to something simpler, the isotropy. Now, here is a picture from Jim Peebles' book, which I like. And that shows this picture of radio sources mapped from, I think, Green Bank, West Virginia, which purports to demonstrate the isotropy of the universe. For a long time, I wondered what that streak across the picture here is. That is actually the Milky Way, because there are radio sources in the Milky Way, which are contaminating our view of the extragalactic sky. And these holes are the unobserved regions which you can't see from West Virginia.
Sorry, Subir, one moment. Ashutosh has a question.
Okay, Ashutosh, go ahead.
Hi, Subir. Okay, if I ask a question in the middle?
Please do.
Okay. If you could go back one slide.
Yes.
Not being an expert, tell me if my objection to the astronomer's objection makes any sense.
Yes.
Their objection is, if I understand it correctly, that since you don't have very good measurements of the distance, independent measurements or the techniques you mentioned, 20% errors.
Yes.
Do I correctly interpret that objection to mean that the small error bar red points, the ones you were discussing,
yes,
could be shifted left or right on the x-axis
yes,
by 20-25%? That's what they're objecting.
Well, they're also objecting to the velocity that you inferred for this object.
So they could move up and down by 20%.
Well, not 20%, less, but there's an uncertainty in that direction as well.
Okay, so but when I heard that the x-axis could be shifted, x-axis position could be shifted by 20%,
yes,
to me that seems to be irrelevant, because the pink curve is so flattish that you move the red points left, right by 20%. It doesn't make any difference to the...
Well, it would bring some of them within the 2 sigma envelope. You see, people I could also draw the 3 sigma envelope, and these would be almost, these two would be taken care of by that. I should say, Ashutosh, this is my personal impression, that people are quite quick to, invoke the kind of particle physics principle, if you like, of neglecting anything that is just, 2 or 3 sigma. but when it serves them. In other contexts, when the evidence is no more than 2 or 3 sigma, it is that objection is not raised. But I think I'm just simply trying to draw attention to the fact that the CFO survey recently has finally achieved some mainstream status by publishing a major study done over quite some time with a whole bunch of people. And the only objection being raised to it now is, as I said, the fact that the distance estimates are uncertain. You hand wave and say there are systematic uncertainties, right? It's always possible to find, as you know very well, systematic uncertainties in other people's work. So, but I hope that more attention will be drawn to this because we really need to nail this. But like, as I said, precisely because this is controversial in that respect, I want to move to something which is simpler. But I see Indranil has his hand up.
Yeah, go ahead, Indranil.
Yes, what I wanted to mention. Can you go to the previous slide on the buffaloes? Yeah. So regarding the Watkins results, like also Whitford et al. Got a similar result, which I put in the chat, and that only went out to 173 over each megaparsec, but it was it was very consistent with the Watkins results. So
yes,
they reported there was excellent agreement. Now, regarding the bulk flows, like, yeah, I've also talked to astronomers about like what concerns they might have. And in general, like the issue of uncertainties in individual galaxy distances. So I should say redshift independent distances, of course. The uncertainties in these are not considered as a serious issue typically because you are averaging over many different galaxies. So even if an individual galaxy has some uncertainty, it shouldn't affect the bulk flow very much. The bulk flow can be thought of as a dipole in the redshift of a galaxy at fixed.
That's right. Yeah, that's what that is exactly what we showed in this paper C11, that you see a clear dipole in the luminosities, magnitudes of, say, type 1a supernovae within redshift of 0.1.
That would be really interesting to look at, of course, with the latest sort of Pantheon data as well.
I have a plot of that coming up later.
Okay. So yeah, so I just wanted to mention that like uncertainties in the distances shouldn't really, like for any individual galaxy, shouldn't really come in too much because of the large numbers of galaxies that are averaged.
I agree with you. I was just quoting to Ashutosh the typical objection that is raised by the typical astronomer. But I agree that it is true that there are correlations. So these error bars are not all independent. For example, the ones which are at smaller distances are, of course, part of the sample at the larger distances. So those correlations have to be taken into account. But my personal belief is that there is something going on here which needs further investigation. And I'm happy that Tully and company have now actually managed to make this issue somewhat mainstream. So
it's very mainstream. I mean, I went to the conference in Thessaloniki recently on cosmology, and the bulk flow. I mean, Watkins was giving a talk there, and the CF4 measurements, which are not the only bulk flow measurements, but these are considered pretty mainstream by now.
Well, I should hope so too. Let me continue with my talk. Yeah. So as I was saying, Peebles' textbook says that this proves the isotropy of the universe. But in fact, if you are moving with respect to the cosmic rest frame, then the distant sources cannot be isotropic for the same reason that the microwave background is not isotropic. And this was pointed out, in fact, by George Ellis and John Baldwin, who interestingly met at a conference at a ex monastery in Crete in 1983. And John Baldwin was undertaking the Cambridge survey of radio sources. And they realized together that the same phenomenon that gives you the dipole in the cosmic microwave background should give you a dipole in the distribution of distant objects because of the combination of aberration, which incidentally was discovered by Bradley, who was the civilian professor of astronomy here. And he, in fact, found this special relativistic effect 180 years before special relativity. And then you combine that with the fact that these sources typically have not a Planck spectrum, but a power law spectrum. So a moving observer samples a different part of the spectrum. And so the number of objects which are above some threshold, if it is falling as a power law, what we'll have is, if I could show it pictorially, if you had an isotropic distribution like that, and you're moving towards the red dot, then the sources get focused in the direction of the red dot. And also, sources which were below threshold in a flux limited survey would be pushed above it in the direction you are moving, and the opposite in the direction behind you. So overall, you'd get a dipole in the sky, which you can see with your eyes here because I've exaggerated it. The actual effect is going to be of order V over C, which is 10 to the minus 3. But there's a prefactor here, which turns out to be 5. So we are talking about a 0.5% effect, a tiny effect. So obviously, to measure a tiny effect, you need a lot of galaxies or radio sources or quasars, and you need them to be at cosmological distances, not nearby. And that data did not actually come along until this millennium. And this particular paper, which took a year to appear for some reason, simply emphasized that this was a consistency test of the FLRW model. You should find the same dipole in the sky in the radio sources as you do in the microwave background, because if they were in disagreement, either the radio sources are not cosmological distances, or the interpretation of the CMB as relic radiation is false, or the third option is the standard FRW universe models are suspect. So I think today we would agree that A and B can be ruled out, that leaves C. Now, I will not go through the whole history of this subject for lack of time. Let me just say that we have essentially conducted this test with a catalog of quasars, which are large enough in number that we can beat short noise, fluctuations that just are random on the sky. And this quasar catalog comes from a survey done by the WISE infrared satellite, operating for many years, both while it was in a cryogenic phase and afterwards in different bands. The advantage of doing it in different bands is that when you do a color plot, then you can pick out quasars as opposed to other objects which are nearby, like stars or galaxies, etc. And in fact, the spectrum of the quasar is also quite distinctive in this mid-infrared band compared to the other objects that could look like them if you could not resolve them. And I should say that this paper our work was led by Nathan Seacrest, who was part of the original WISE team that put together this catalog. And essentially, what we want is a flux limited survey. In other words, we say that we see all objects above some given flux with 100% efficiency. This is the actual completeness level that you see here. It's very close to 1. We do look at this survey very, very carefully. We have looked at it for about 4 years now. And in fact, at one point, we looked for a correlation with the scan pattern of the satellite, which you would expect an ecliptic latitude. And in fact, there is a small correlation, about a 1% effect, which we could allow for. When we do all that stuff and create a sky map, you see what on the left-hand side, a picture of about 1.4 million high redshift quasars. How do you know they're high redshift? Because part of the sky was also mapped by the Sloan Digital Sky Survey in the program called EBOS, which was for measuring baryon acoustic oscillations. And they measure spectroscopic redshifts with exquisite precision. And that distribution is shown here. As you can see, it peaks above 1. So essentially, we can say for definitiveness, 99% of these objects we're looking at are at distances sufficiently large that the universe is effectively homogeneous on that scale. And we need not worry about what is called a clustering dipole, which is that accidentally some object might be close to us in some random direction and give us a large dipole because of that. When we smooth that sky, we get that characteristic dipole pattern. And now what we do is we take these 1.4 million objects and we know their flux distribution and spectral indices. So we run Monte Carlo. My collaborators in this are Nathan Seacrest, Mohammad Ramiz, who is at the Tata Institute of Fundamental Research, Sebastian von Hauseger, who is a postdoctoral fellow here at Oxford, and Roya Mohai and Jacques Collin are astronomers. Roya Mohai is a relativist, and Jacques Collin is an astronomer at the Institute of Astrophysics in Paris. We've been working together for some years on this and related topics. Now, if we take that distribution and we generate Monte Carlo simulations from them, we create mock skies, and then we can ask in the mock skies, what does the dipole look like? Well, we find that the actual dipole that you see on the sky, which is this red triangle, is in the same direction within that error circle as the cosmic microwave background dipole marked by the star. But the amplitude of what we see is significantly higher than what you expect from those mock skies. It is about a factor of 2 higher. And the discrepancy is now very large. As you can see, the tail of this distribution does not even reach up to there. Now, when we did this earlier, there had been a claim already made on the basis of the NVSS catalog of radio sources. And that was not by itself statistically significant, although that was indeed the first time that people had said there might be an issue here. If we combine the NVSS and the WISE data, which are 2 independent samples, they had only 80 objects in common, which we threw out, and we mask it. For example, here is the 408 megahertz map of the galaxy used to mask it out. Remember that streak in the Peebles picture, we don't want that. And then when we combine them, we find that the 2 dipoles are actually consistent. And they point towards a direction which is close to the CMB dipole. Actually, the agreement between them improves if we subtract out the CMB dipole first. The CMB dipole, you recall, is half of what we are seeing. Now, in the first paper that we wrote, we in fact did the simulations requiring the dipole that we are looking for to be within striking distance of the CMB dipole. Otherwise, that is the expectation. But we decided now to be even more generous and let it point in any direction it likes. So what you see here is the dipole offset in degrees from the CMB dipole direction versus its amplitude, and the expectations for the WISE catalog on the right and the NVSS catalog on the left, and the white crosses mark the actual data. The other things show the expectation in the standard model. So if you combine these 2 data sets, we find that the standard cosmology expectation is rejected at more than 5 sigma, which is psychologically, at any rate, what is important in fundamental physics for taking something seriously. In fact, we did a very transparent frequentist methods. So we ran 10 million simulations, and 4 of them got up to the amplitude that we are looking at. So that's a p-value of 4 10 to the minus 7. It's literally throwing darts at a board. But you can, of course, do a more sophisticated Bayesian analysis, which has been done by an independent group. And they ask a slightly different question and get therefore a slightly different answer. Their significance, they claim, is 5.7 sigma. Now, it's important to emphasize that this is not a clustering dipole. And in fact, the best way to see that is to do an angular power spectrum of this data, which has been done by Tiwari, Zhang, and Nusser. And what they have done is essentially calculate the multipoles of the distribution just as you do for the CMB. The dipole that we measure is up here. Okay. And what they find is that the power spectrum on small scales is consistent with what you expect from the standard theory of structure formation, right? At very high multipoles, in other words, at small angles, you get good agreement. In fact, these authors think that they can even tell the deviation from the linear spectrum to the nonlinear one. And from that, they can even read off the bias factor, which turns out to be about 2, which is what you expect for these quasars. But the important point is that you have excess power on large scales. And this is the expectation of the clustering dipole down here. And what you measure is way above. So it clearly is not a clustering dipole. Subsequently, various radio catalogues have have become available from the precursors to the square kilometer array, in particular from this RACS catalog. And using these, Dominic Schwartz and collaborators have been able to show that the radio galaxies also independently give about 4.7 sigma deviation from the black line, which is the standard model expectation. How has this anomaly been reacted to by the cosmology community? Well, I will leave this to Jim Peebles to say. He wrote a review recently of anomalies in cosmology, and he says of this dipole anomaly, it's as well established as the Hubble tension, yet the literature on it is much smaller than the hundreds of papers about the Hubble tension. I expect the difference is an inevitable consequence of the way we behave. Now, I have no idea what he means by that. I'll leave it to you to figure that out. All I can say is that some people have shown interest in this finding, and they have started looking at possibilities beyond FLRW, which are very hard for the obvious reason that Einstein's equations are very complicated. You need a great deal of symmetry to solve them, and FLRW is popular for that reason. It gives a simple equation at the end, which anyone can solve. You can confront it with a wide variety of data. Whereas if you let go of that, then you have all kinds of complications. However, I want to turn to one implication of this observation, which is actually rather important, which has to do with the acceleration of the universe and the inference that the universe is therefore dominated by vacuum energy, which is driving this acceleration. Now, it was pointed out by Christos Sagas, who is the guy who organized that conference at Thessaloniki that Indranil mentioned, who we are working with. He had pointed out that if we are not actually in the cosmic rest frame, but we are embedded in a bulk flow as we appear to be, then the bulk flow itself carries energy momentum. And you need to take that into account and solve the Raychaudhuri equation in order to interpret cosmological data. And he finds that, to cut a long story short, if you look at the deceleration parameter as it would be inferred by an observer, a so-called tilted observer, to use the language from George Ellis, that observer would see a value of the deceleration parameter that is modified by this bulk flow, such that if the bulk flow is converging, as it appears to be, you could in fact have a situation where the overall, globally, the universe is decelerating, but locally you think it is accelerating. Now, I first met Christos quite some time ago, about at least 15 years ago. I heard him give a talk about this, and I asked him how we could test this idea. And it turned out that because very little is known about our bulk flow and its properties, you can't really calculate from first principles how much this effect should be. But he agreed that the clear prediction of this is that the acceleration, if it is a phantom acceleration, should be seen in the direction of the bulk flow, in the direction of the CMB dipole, which is what the two are related. So we took the supernova data, which was publicly available. It only became publicly available in 2014 in the joint light curve JLA catalog. And we did a cosmographic analysis, which is, we don't assume a model. We just do a Taylor expansion of the luminosity distance with redshift. So the first term is the Hubble expansion. The second term is the deceleration, etc. To minimize parameters, because we have only 740 supernovae, we allowed the deceleration parameter to have a monopole component and a dipole component. And then we use a maximum likelihood estimator to interrogate the data. And the data then tells us that it is actually the acceleration that is inferred from the supernovae is consistent with being almost entirely a dipole with an amplitude in this units of -8, as opposed to the monopole, which is only -0.2. So it is about 50 times bigger. Here is the standard ΛCDM model, which is the monopole and no dipole. And we rule it out at about, I think, 3.9 sigma. Now, with just 740 supernovae, you can't pick out the direction very well, but it is consistent with the CMB dipole, as you see here. So which says that the acceleration that you are inferring from the type 1a supernova Hubble diagram is in fact directional. Ergo, it cannot be due to a cosmological constant in the vacuum. And it in fact suggests that it is an artifact of our being located in a deep bulk flow. Okay. Now, Indranil asked earlier about Pantheon Plus, which is the latest supernova catalog that has about more than twice as many supernovae as JLA. And this is the distribution in redshift of Pantheon Plus as opposed to JLA. You can see that they've added a lot more at low redshift and a few more at high redshift, but basically they're almost within redshift of 1. So our Taylor expansion is quite valid. And you see here that the trend that we had seen earlier is in fact true, regardless of what frame of reference you do the analysis in. We had done the analysis in the heliocentric frame, but then people who didn't like our results said, well, you should be doing it in the CMB frame. However, as I've just shown you earlier, the fact whether a CMB frame in fact even exists is suspect, because if you boost to it, we still find that the quasars and radio sources are not isotropic in that frame. So people make peculiar velocity corrections on top of the CMB frame to try to take out that anisotropy. But we find that whatever you do, in whatever frame we analyze the data, including the frame of the local group, which is perhaps the closest to that of a free observer, such as the tilted observer in Sagas's model, we see a strong dipole anisotropy. The reason why it can be either positive or negative is because of the reason I gave you earlier. Our motion in our galaxy is opposite in direction to the CMB hotspot. So if you are in the heliocentric frame, you see a dipole of a certain sign. If you move to the CMB frame, you see the dipole of the opposite sign, right? And you see the directions are all consistent with the purple star here, which is the CMB dipole, or the bulk flow direction, which is this brown patches here. They're not quite in the same direction because the bulk flow has not converged by the time you get out that far. You might well ask what happens if you go to 300 megaparsecs or 400 megaparsecs. The answer is we don't know because nobody has got the data. But the data will come soon, hopefully from the LSST, from the Legacy Survey of Space and Time, to be conducted on the Rubin telescope. And then you will know how exactly these arrows are traced in redshifts. I should say that, as in passing almost, that the Hubble parameter, now that you have more supernovae, we can allow the Hubble parameter to also have a monopole and a dipole. And as you expect, it also has a dipole anisotropy of 2 to 3% in the very redshift range where the calibration is being done of the type 1 supernovae to the C feeds, which are locally calibrated with parallax measurements, etc. So in other words, in the redshift range where it is kind of being assumed that you have already reached the Hubble flow, we are clearly seeing an anisotropy due to our local bulk flow. So that might have a bearing on this famous Hubble tension, which is supposedly a discrepancy of a few percent between the Hubble parameter measured to 1% locally, and that inferred from the microwave background. So let me come to my summary. I think I've taken my time. As Weinberg rightly said in his book, you had to start with the simplest option, and that was the cosmological principle, and there was no data then. But now we have the data, so we should really test now the fundamental assumptions of homogeneity and isotropy and not focus on this so-called precision cosmology of the model parameters. The discrepancy that should cause us to pay attention is this local bulk flow, which is not dying out as you should expect it to do in the standard picture of structure formation. Now, of course, this could be an anomaly. In other words, in a Gaussian random field, anything can happen at some probability. Question is, with what probability would our neighborhood happen? We have actually answered that question by interrogating the so-called dark sky simulations, which is the largest n-body simulation done of the universe. And we find that, in fact, our particular local bulk flow is unlikely at the level of exceeding 4.5 sigma, a similar number to the one that was given by the Watkins et al. Paper. The implication of this is rather important because all the analysis of cosmological data that is being done now assumes isotropy and homogeneity and ignores the fact that the bulk flow is anomalous. And in fact, I have shown you that the inferred acceleration of the Hubble expansion itself is anisotropic and therefore cannot be due to a cosmological constant. Very worryingly, the rest frame in which distant quasars and radio sources are isotropic does not coincide with the rest frame in which the microwave background is isotropic. So this is a challenge to the very assumption of FLRW metric. And that would be a real issue, a real problem, because ways beyond it are not easy to see. But in principle, with enough data, we can actually undertake a program that was suggested long time ago by Alice and Stoger, which is to actually construct the metric directly from the data rather than base it on a philosophical principle. Of course, in practice, you need to, it is good to perturb around an assumption. So you could start with the FLRW metric and use the data to perturb around it. And in fact, it turns out that modern advances in machine learning and so on would in fact allow you to do that in a sensible way, because you need to deal with huge bodies of data that are soon coming from forthcoming missions. And in principle, this idea of constructing sort of bottom up is not as far out as it once seemed. Let me give you a taste of that. Sorry, I don't think I have the slide here now. I was going to show you a picture of this LSST Rubin. In fact, what I have here is a poster for a conference that we held recently in London at the Royal Society, where some of these issues were discussed. And you will find the videos of all the talks at that URL, which is written there. And let me just end by saying that this is, of course, was designed to tell you what the observations are. But I have also written an essay on this for a more general audience, including people who are not cosmologists. And if you are interested in that, it's available online on Inference magazine, which is edited by Shelley Glashow and other physicists. And they wanted to know what the data is actually like, because one of the problems in cosmology I find today is that people who are interested in fundamental physics are not as familiar with the techniques and tools used in cosmology to make inferences as they would like to be, because there is obviously a lot of complexity involved and it takes years to learn these things and to penetrate the jargon. But I think it is useful to be able to do so, because these are fundamental issues that affect us all. So thank you. I'll stop there.
Great. Thank you, Subir, for a very clear and very important lecture. I hope the recordings that will become available induce more people to take this matter seriously. We have a few hands up. Indranil and then Andrew had a question. Indranil, go ahead, please.
No, I think he already asked his question. His comment was about Whitford. Oh, sorry. I see a new hand. Go ahead.
Yeah, can you go back to the previous slide? Yeah, so I just wanted to ask, do you know, sort of querying ΛCDM simulations and taking mock observations of supernovae, what kind of values for the QD you would infer if you, for comparison with, the cyan points in
you are asking accidentally what can you get for QD?
Yeah, because you clearly infer some non-zero QD in ΛCDM because of the structure in the universe, right? And
well, as I said, you do not get, so this is arising out of our bulk flow, and our bulk flow is quite anomalous in ΛCDM. So it would be extremely unlikely.
No, but that's your interpretation. It's arising out of the bulk flow. That's the most likely explanation. But this
but
isn't.
the simulations are not of supernovae, Indranil. That is what you have to recognize.
Yeah, but you could like
simulation-
populate them with some galaxies randomly with supernovae, and maybe
that nobody would believe that, because we would not know how to actually do that. In order to do that, you'll need a fully baryonic, all bells and whistles simulation, which
I
nobody has
see,
got, right?
because of the clustering properties of
And
the
even if
supernovae.
we made the effort to do that, people who don't want to accept the answer will not accept it anyway. So
No, of course not.
so my point is simply that the bulk flow itself we can address, because that is being driven by dark matter. That is what most of the gravity. Sorry, I should say whatever is causing the bulk flow is anomalous in the lambda CDM theory of structure formation at something like 4.6 sigma with the presently quoted uncertainties. Right.
Yeah, fair enough. So you think the bulk flow is a more promising test? Fair enough.
Okay.
Okay.
All right. Go ahead, Roger.
Oh, yes. Very nice talk. I enjoyed it very much.
Thank you.
There's an issue which comes up when we consider conformal cyclic cosmology. I know it's a very different topic, but we do find a very significant, well, I won't use the word significant because it probably, you have to, it looks very significant non-isotropy in the distribution of effects. I mean, we claim we're looking at, I'm talking about the collisions between supermassive black holes.
Yes.
We take the view these are taking place in an eon prior to ours.
Yes.
In gravitational wave signals, and these would produce big rings in the cosmic microwave background.
Yes.
Which one can, I mean, I don't know of any other explanation for, but I would refer to a paper that Vahe Gurzajan and I published in 2016, I think it was. It's got a funny title connected with the Fermi paradox, but that's not really the point I'm trying to make. There's a very nice picture there of the seeming sources of these gravitational waves, which the sources would be in the previous eon. And it's very inhomogeneous. And you see huge clusters of these events, whatever they come from. I mean, you've got a different theory. You might say they come from something else, but you have to have an explanation for why they're so extremely inhomogeneous. It could be, and I think it's quite likely, that there's a connection with quasars, because one of the most significant regions that we see seems to correspond to these very early quasars. I'm not very familiar with the observations, but there seems to be some correspondence with that. I'm just trying to make the point that we do. I mean, it just seems to be consistent with the sort of thing you're saying, that the cosmological principle isn't perhaps as strongly respected by the universe as we might hope. And we do see very strong deviations from this uniformity in the observations that we make.
I'll have a look at that paper. Thank you for referring to it.
Yes, this is one by myself and Vahe Gurzajan in the European Physical Journal of, I think it's 2016.
I should say, however, Roger, that I'm not very optimistic about finding patterns in the CMB, because when you look at how the CMB maps are actually made, which is a rather complex process of correcting, well, first of all, I don't know if you're aware of this, but the maps that are made by Planck, for example, with the high frequency instrument, because that satellite was at so-called Lagrange point 2, it was pretty seriously damaged by cosmic rays, which are not excluded by a magnetic field there, as they would be if the satellite had been in Earth orbit. And because of this, a great degree of interpolation had to be done between the damaged pixels in order to recover the data, which they did very successfully. And then there was, you have to destripe, and then you have to do the map making and smoothing and so on. And unfortunately, without being privy to the various detailed processes by which the observers did this, it is hard to calculate. I mean, it is not an ideal experiment, if I could put it that way. I do not wish to obviously cast any aspersions about the experiment. All I meant is that it would be much simpler if one could take an hypothesis such as yours, run it through that pipeline, and ask whether the answer looks like what you finally get. The reverse process is much harder to do. That is to say, to determine the significance of a particular ring or a pattern that appears on the sky. It is much harder to establish how likely or unlikely that is without knowing the details of the process by which that map was made. And this is something that I have actually thought about a bit because I did hear you talk about this a few years ago, and I talk to people I know who look at this CMB map making seriously, and I'm afraid we came to the conclusion that we would need to do this kind of a, start with the theory and predict the answer, and then compare that with the answer on the sky, as it were.
Yeah, well, we predict that these rings should be there, but of course,
yes. So one would like to do that. I'm saying that the motivation is certainly there, but one would like to do that. But you can't. But just by looking at the picture of the CMB that is shown, it is hard to make out if there are actually rings on there or not. I'm not talking about your expectation, but about the actual CMB map.
Well, yeah, I mean, one can raise issues, but I haven't really seen these issues addressed.
Well, I agree. People ought to address them more seriously. But we can talk about that later. I could tell you a bit more about it. I just wanted to get back to. I thought Andrew Hamilton had his hand up, and I think I might have.
Yeah, Andrew had the question. Andrew, go ahead, please.
Yes. Thank you very much, Subir. That was a really fascinating and challenging talk, and I'm trying to process, because you of course know much more than I do about all of the details that have gone into this. I'm trying to process how it could be that there is so much large-scale structure in our universe in a sort of semi-local sense, as compared to what one sees with the cosmic microwave background power spectrum from Planck, which seems to indicate not so much large scales, not so much. But that wasn't my question. My question was about Jeremy Darling's work. He is in our University of Colorado, Boulder, and he's been very interested in trying to measure stuff at high precision.
Yes.
And in particular, looking at things like, is there any variation of alpha at large scales? Anyway, he's a very careful person. And he concludes in this paper in 2022 that there is no discrepancy in galaxy and CMB dipoles. And he mentions the measurements of other people. I'm not saying I agree with it or don't agree with it, but you're probably much more of an expert than I am.
Well,
would you be able to comment on it?
I certainly can, because in fact, my colleague Nathan Seacrest discussed this matter with Darling in some detail. What Darling did was to take two radio catalogues. One is called VLAS and the other is called RACS. RACS is a precursor to SKA. So they are at two different frequencies. So what Darling wanted to do was to create a full sky map, because any particular radio telescope on the Earth, as you know, can only see about, at best 40% of the sky. Unfortunately, if you combine two catalogues made at different frequencies, they have, so if you have a catalog which is at a higher frequency, because the spectrum is a falling one, the flux is falling with frequency, you tend to be biased towards hard spectrum sources. And if you have a lower frequency, then it would be biased towards steep spectrum sources. So then if you combine them, then the assumption of a common spectral index, which enters into that Ellis-Baldwin formula for the two, that has a potential for becoming biased, right? In fact, the way he did the analysis, what we did was to take the two catalogs separately and show that the dipoles from the two catalogs separately are not consistent with each other. So his combining them and trying to infer an answer from them is therefore not valid without addressing the issue of the incompatibility of the two subsamples, right? And secondly, actually, the title of his paper was quite correct, but the title was a bit misleading, because if you look at the uncertainties that he actually infers for the dipole, they are indeed consistent with the microwave background, but they're also consistent with what we found. Okay, they are big enough to encompass anything. In other words, it was not a particularly useful measurement. Right? So you can see that right in the abstract of his paper. Look at the error bars there. Right. So it's we are talking about the difference between velocity like 370 kilometers per second or something about twice that, say 700. Right. In fact, what he finds is something with the error bar that is large enough to be consistent with both. But that is really coming from the fact that the two subsamples he uses are not consistent with each other. And we think we know the reason why, because it has to do with this bias that is there in the VLAS catalog, one of the two that he used. If you like, I can give you a detailed, send you a detailed answer, which is what we sent to Darling. However, unfortunately, much of the discussion we have about these things with people, they never get published. They don't get into the public domain. But you might like to know that we are right now writing an invited review for RevMod Phys, in which we comment on every paper that has tried to make a dipole measurement and the systematics in those individual papers to provide a fuller picture of all the ways in which one can go wrong. And there are, of course, many ways to go wrong in trying to do this. We would be very happy if somebody could tell us in some way that we have gone wrong. And so far, nobody has done that.
Thank you.
Yeah.
Thanks.
So some years ago, there was a talk of an axis of evil in the CMB distribution.
Yes.
What is the status of that result currently?
Well, that result has not gone away. It was based on the observation that the quadrupole and the octupole in the CMB, which are both anomalously low. In fact, there is no power in the CMB for separation angles over 55 degrees. There's basically no power. But you could perhaps understand that because of the position in which we find ourselves in a Gaussian random field. I mean, goes by the name of cosmic variance. But nevertheless, that anomalously small quadrupole and octupole, it turns out that they are aligned with each other, which they have no reason to be. And they're aligned in a funny way. Actually, it is not so much the axis of evil. That was a misnomer. I mean, Joao Maguejo, who coined it, obviously did it to tease geopolitics of the time. But it is, in fact, a plane of evil, because it is not the L equal to 0 modes which are aligned. It is the L equal to plus minus M, M equal to plus minus L modes that are aligned, right? So, and the thing that people got suspicious about with regard to that is that it seemed to be have something to do with the ecliptic plane. The ecliptic is just the plane of orbit of our particular way that we are moving locally. So you don't expect that that has anything to do with the universe at large, right? And so you think of systematics like, I don't know, extinction by dust in the solar system, which would have something to do with the ecliptic thing, or the scan pattern of the particular satellite that often is something to do with the ecliptic plane. But the fact is that those anomalies still stand, and if you put them all together and you ask some question like, how likely am I to see this, you get some answer which is between 3.5 and 4.5 sigma, depending on what question you ask. Unfortunately, these anomalies will not be resolved with more or better data from another fancy new satellite, because they are at large angles. So at any multipole L, you can only make 2L plus 1 independent measurements. Right. So, for example, for the quadrupole, you just make 5 independent measurements, whereas for multipole of 200, you are making 401 measurements. So the variance is much smaller. It goes as 1 over 2L plus 1, and so at small multipoles, large angles, the possibility that our particular vantage point is determining what we see is much higher, right? And I actually always find it amusing that people are quick to invoke cosmic variance to explain why we don't see any power on the sky at large angles. But at the same time, they are very upset when you say we are violating the Copernican principle. We have violated the Copernican principle long ago by accepting that we live in a fluctuating density field.
Yeah.
We are not, we are not special, but we are where we are, right?
Yeah. So suppose I say that I have a fundamental physical theory of unification, which suggests that there's a preferred plane in space, which around which there is a, let's say, axial symmetry. Would that claim be supported by this so-called plane of evil?
Well, as I just explained, it would be difficult to establish any fundamental theory when the observations are subject to the possibility of bias because of this cosmic variance. In other words, you could never make it stick because you could always argue. I think actually Andrew is perhaps better informed than I am with regard to this. That basically you are. It is very hard to fight cosmic variance. In principle, it can be done in the sense that once you have established, let's say that the low quadrupole is because of our being located in a particular place in the in the background, that then should not be moved again to discuss a different anomaly, let's say the quadrupole, which is independent, right? I mean the octupole.
Octopole.
So in principle, you could, if you actually took this cosmic variance business seriously, try to pin it down by several independent sets of data, each of which is subject to cosmic variance, but in different ways, and thereby try to determine exactly what our position is, right?
Okay, and so suppose there is such a fundamental plane, is there some evidence for it in large scale structure?
Well, these structures that we are talking about in the CMB, these are of course at very, very high redshift you're talking about, right?
Yeah,
You're talking about
I
the
mean
dark scattering circuit.
galaxies and quasars.
No,
Yeah.
galaxies, that's the thing. We don't really know because we haven't mapped it out.
Okay.
So I showed you the map of quasars, which are peaking at about a redshift of 1.2. That is the largest catalog we have today. Okay, about 1.6 million so far, right? The largest map, radio sources, we don't actually even have redshifts for them. Only about 150 radio sources so far we have actual redshifts for. Although with Gaia, now by cross correlation, we are finding a lot more. But even they peak at about similar redshift, and there are only, I don't know, of order a million of them.
Okay.
To answer your question, one would really need to map out the universe, do tomography in redshift all the way from locally, say redshift of 0.1, out to redshift of 2.
Okay.
And what we have today is the DAISY instrument has in fact done a marvelous job. It has measured the redshifts of, I'm told ultimately they'll measure tens of millions. They already have of order 10 million redshifts in the can. But that is only over the patch of sky that you can actually see from the Kitt Peak
Right.
telescope in North America. And similarly, the LSST will be done from this Rubin telescope that is being constructed now in Chile. That will see a different patch of the sky, also about 40%, right? In the near future, there is a exciting proposal on the horizon. Not a proposal; it's already been funded. It's a experiment called Sphere X, which is being led by Caltech, and this will in fact map 4 pi sky, right? It will not measure spectroscopic redshifts like DAISY, which is very expensive and difficult to do, but it will map the whole sky. And I think for the kind of tests that we are thinking of, Sphere X will be an ideal instrument. And I was quite impressed to learn that it is already now at the point where it is being tested at JPL. So it might fly next year, and I look forward to that.
Excellent.
I just want to make a comment because I mentioned the DAISY data. The DAISY papers, which have come out analyzing the 5.6 million redshifts that they have got, start by assuming isotropy and homogeneity. Their entire inference about the equation of state for dark energy that actually changes, deviates from -1, etc., assumes isotropy and homogeneity. So in fact, when I questioned people in DAISY as to why with so many million redshift they could not test with their own data, if, for example, the BAO signal varies with direction, I'm afraid the answer was that they haven't done it.
Okay.
I cannot say whether they are doing it or will do it or are interested in it because I'm not in that collaboration. But I must say I did find it rather disappointing that even when we have the data, you still continue to make an assumption that was made when there was no data.
Yes, yes, thank you. So thank you.
Can I ask a question, Professor Subir?
Yeah, we have three questions lined up. Go ahead, Jitu.
Yeah, go ahead.
Professor Subir, Dennis Sharma once wrote a paper on origin of inertia, in which he claimed if we add up all the gravitational potential in our universe, we will get c square. Is it still relevant today?
Well, actually, I think Roger perhaps is better qualified to comment on that. But when I first met Dennis, he was quite interested in Mach's principle, which is what you're alluding to. But I think as far as I know, he
actually
went
there isn't there a 20 Mach principle or something, which a paper written by Samuel and J. Bondi.
Yes, that's right. So he was very fascinated with Mach's principle, and in fact, that book that I quoted from is largely devoted to Mach's principle. But I don't think. Well, as you first of all know, Dennis passed away rather prematurely. So I didn't,
There is also another story which Dennis met Einstein, and Einstein said, "Oh, I have given up Mach's principle," but Dennis wasn't.
Actually, as far as I know, Dennis stopped believing in Mach's principle, although he certainly encouraged discussion and thinking about it. And in fact, I did tell Dennis that the thinking that we have in particle physics is that the origin of inertia is the coupling to the Higgs field which pervades the universe. It's a local phenomenon. It has got nothing to do with action at a distance. But let's not get into that now. Can I answer the questions relating to this talk, and then we can come back to
yes. David, go ahead, please. David, go ahead.
Oh, okay, thank you. Thanks to Jenda, and thank you, Subir, for the talk.
Yeah.
Hi. So early on, you mentioned the Friedmann equation and how the Hubble constant sets this kind of scale in that equation.
Yes.
And the fact that we kind of measure the dark energy of that scale as a kind of a warning sign. But we also know that dark matter energy density is of that scale, and the visible matter energy density is within an order of magnitude or so of that scale. Would you see those two things as coincidences, or are they also problematic, or are there reasons to expect those two things to be of that scale?
Well, that's a good question. What you're saying is basically all omegas are defined in ratio to h naught square. And therefore, you have some dimensionless number resulting from taking the ratio of the energy density to that given scale, right? But the fact is that there is a hierarchy between them. Visible matter is, 6 times smaller than dark matter. Dark matter is a factor of whatever it is, 6 times smaller again than dark energy in terms of. So it's not a huge hierarchy, but there is a hierarchy. But the fact that they are within spitting distance of each other is necessarily required. If you want to make up a triangle with 3 lines, then they have to fit together to that extent. So that is not by itself surprising, right? What I meant is that the scale of the energy density of baryonic matter is determined with the number of baryons in the universe. That's something you can count, right? It's observable. Similarly, the amount of dark matter, in principle, you can determine it if you could measure dark matter by non-gravitational means one day, or whatever. You can count them. You can actually measure it. But dark energy is, I'm saying, being inferred. It is not actually being measured. It is just being inferred on the basis of that Friedmann equation. There is no direct evidence for dark energy, to my knowledge, in any observation. Much, which is a surprising and perhaps provocative statement, but believe me, it is true. Everything that people think, for example, the last time I gave this talk, somebody said, what about CMB lensing, which is gravitational lensing of the CMB? It causes a little shear in it. That's direct evidence for lambda. It is not. what you see in the CMB, the gravitational lensing of the CMB, the integral that gives you that is an integral over the growth of structure from today back to the last scattering surface, right? Any process that gives you that same integral will give you the same effect. It doesn't have to be lambda. Lambda is one possibility, right? But it could be something else as well. So in other words, the following statements are true. Lambda is consistent with all the observations, but so are other possibilities. Okay, so there is no evidence for lambda as the unique cause for all these observations that we are making. Right? A unique cause would be the measurement of some distinctive property of lambda, namely the fact that it has negative pressure. That measurement has not yet been made. The data are consistent with lambda having negative pressure, but it has not established at 5 sigma, let's say, that we are 2/3 of the universe is made of something with negative pressure.
Okay, but you think there's an element of coincidence about the fact that visible matter and dark matter have the same order of magnitude and within an order of magnitude of this scale?
I think that, well, I personally, if you want to think about dark matter and particle candidates, I think that that coincidence is interesting because it suggests a common origin for both of them. And there are many mechanisms for that. I've just seen in the chat, Indranil Vanek has pasted BAO measurement show the expansion rate is accelerating. No, they don't, Indranil. I just said that all the BAO data is analyzed assuming Friedman, Lemaitre, Robertson, Walker. In particular, they do not address the question of whether the BAO signal is the same in every direction. So they don't even test that idea. So you can't, it's a measurement, it's a geometric measurement.
Yeah, Indranil, could you kindly wait? We have others participants lined up. David, anything more?
No, that's fine. Thanks very much. Yeah, thanks, Subir.
Okay, Anastasia, please go ahead.
Yeah, thank you so much. So my actually question is related to what Indranil wrote in the chat. So I think that when you talk about consistency with lambda, I think that maybe, yeah, we don't kind of have as good arguments actually against lambda as we do have against dark matter. So my question is, when you talk about problems with the cosmological principle, have you considered new HDM that Indranil was working on and others like Moritz Hausbauer and Paavo Krupa, so the alternative model that doesn't kind of have the same problems with homogeneity and isotropy? So the solution of the Hubble tension through the local void? Because I think that your concern is that you start cosmology from this general kind of philosophical principle, right?
I don't. That is the standard cosmological model. It's not my model.
But no. But your concern is that you shouldn't do that, right?
No, my concern is that we use that model to infer that 2/3 of the universe is made out of vacuum energy at an unphysical scale. That is my concern.
Yes.
And that is not addressed by anybody as far as I know. The work by Indranil and collaborators that you alluded to, I'm very familiar with them. They are more concerned about the nature of dark matter.
Yes,
they're not addressing the matter of dark energy, which is quite different.
No, yeah, but still, the local void-like solution for the Hubble tension, this would like have to be somehow affecting the dark energy, no? Or do you think that it's
no? That has got nothing to do with dark energy. It might have a bearing on the Hubble tension. That is a well-known. That is something that I alluded to earlier when I showed the local universe and the fact that it must surely matter where we are located there, whether in a high-density region or in a void. And the fact that the discrepance that the Hubble parameter could be, in fact be different in different environments according to the local matter density. This is indeed an old idea. And as we map out our local environment better, this possibility has been raised repeatedly that a local void is biasing our inference about the large-scale properties of the universe. However, there is an issue astronomically, which is that the idea of a local void was actually in a paper which included Adam Rees amongst one of the authors. In fact, they pointed out that various problems are sorted if there was a local void. But then it turns out that there is a degeneracy between a technical point here about the amount of extinction that you have in supernova light curves. which could be either due to a jump in the Hubble parameter at the local void or due to intrinsic absorption in the sources. And they concluded sometime later that therefore the supernova data ruled out a local void, which nevertheless counts of galaxies, as has been done by people like Tom Shanks and collaborators, or by the Hawaii group, Len Cowie and collaborators. They continue to say that they find a underdensity of objects, actual physical objects, which implicate a local void. So I certainly am quite interested in the idea, but that will not do away with dark energy. That only addresses this issue of the whether the Hubble parameter, what the variance in the Hubble parameter is. That it only does that.
Yes.
Which is a different problem. In fact, as I hope I illustrated, the Hubble parameter you should not really even expect to be, it's like asking what is the value of the radius of the Earth. The Earth is not a sphere to an accuracy of 1%. So you can't actually ask what the radius of the Earth is to an accuracy of 1%. The Earth is actually a geoid. It deviates from its spherical form by 150 to 200 kilometers. And so the question itself is not well posed. We can approximate it by a sphere and we can talk about that radius, but then that is not a 1% measurement. And similarly, the Hubble parameter in our neighborhood, the contours, if you like, are not nicely smooth and spherical. They are highly distorted, right? In fact, Andromeda, like I said, is falling towards us. So it's kind of, the contour will have a little hole in it. It's only when we get out far enough that these things become smooth and spherical. And the point is that right now, I don't think we have got out far enough for these local irregularities to have disappeared. And we are calibrating the distant supernovae to Cepheids in a redshift range where we can clearly still see evidence of the local bulk flow, right, which is caused by the same inhomogeneities. So you're really looking at different, this is the classic looking at different sides of an elephant and trying to piece together the whole object from it.
And that's what I'm saying, that instead of starting with the cosmological principle, if you want to start with actual evidence, then you have to start with what you talk about, and then you also have to start with the fact that there is this underdensity, right?
So in this program that I mentioned at the very end, this idea of actually trying to construct the metric for the universe from data, that would be indeed the program, to actually use data to do that. But that is not a trivial exercise, as you might imagine, right? So
what I would imagine is that every data is read through a theoretical lens. So you have, yeah, and like Adam Rees was talking about this void, and he said the void is impossible. Why? Because it's not possible within the standard model of cosmology.
You are absolutely right. There is that degree of confirmation bias we unfortunately are subject to in cosmology. So in ΛCDM, the variance of the Hubble parameter from point to point is of order 1%. So therefore, if you believe that ΛCDM is the model, then you don't expect to find variance more than that. But you should not forget that that is only a model. The real universe is the real universe, right? So the question then is,
it seems to be like ΛCDM. So.
Well, it does look like ΛCDM in many respects, but in some other respects it does not. And I'm focusing on the ones in which it does not, because that is where the cracks will appear. And our experience, at least in particle physics, is where the cracks appear that we make progress. Right? We can spend all day discussing all the successes of the standard model of particle physics. We don't do that anymore because we know that it's a very good model. We only focus on where there is some tension, right?
Yeah. On that note, Subir, I'm surprised that you seem to be so favorably inclined for dark matter. There's no evidence, and the assumption of dark matter creates lots of problems on astrophysical front. So why not modified gravity at least be considered?
Well, when I lecture on dark matter here, I do in fact spend a whole lecture discussing the evidence that I have learned about from Milgram and others over the years, and by pointing out that actually that there's also again new data on the horizon very soon. So the possibility that Okay, let's start. The thing that I actually found most compelling about MOND was the Tully-Fisher relation. And
Yes.
actually, I set a student to work on it years ago to see if it could somehow emerge from this lambda CDM theory of structure formation. You get close, but not sufficiently close. You get a slope of 3.7, but with much more scatter than what you actually observe in the real slope, which is 4. So that way it failed to do. And of course, this the usual argument which Indranil outlined in the talk that he gave a few weeks ago, right? That all the spiral galaxies and indeed even the ellipticals fall on this universal curve, etc. This has all been well known for a long time. I've followed the story along with astronomers. There was somebody at Groningen who, in fact, had studied this extensively. He measured all the rotation curves. So I know all the evidence. The reason why I still talk about dark matter is because just as with dark energy or lambda or the standard cosmological model, if you cannot find an alternative theory of gravity that can account for a MOND-like behavior at low accelerations, then you are not going to be able to convince the physics community to switch gear. However much the evidence in support of there being no dark matter or no need for dark matter. And I think Indranil's talk itself made it quite clear that there are serious problems in trying to find a alternative theory. The usual candidates that were constructed, Teves and so forth, and all of them, and when looked at in some detail.
I must point to my own new work, the theory of dark electromagnetism. It's a U1 interaction, which is the analog of electrodynamics, Maxwell's electrodynamics. The dark matter candidate is actually a massless dark photon. It's the Coulomb condensate of the dark photons, which has Mondian behavior. We have a paper on the network. I'll send it to you. So there
well, I'll say this, that the attention that has been paid to MOND has resulted in a very healthy development, which is that people have taken the experimental observational data seriously and are now challenging models that are put forward seriously with data. It's not just a matter of fitting a rotation curve anymore, right?
Yes.
And I'm saying that is I think a very healthy step in the development of the subject. The reason why particle physicists are wedded to dark matter is very simple. It is a very natural expectation if there is new physics beyond the standard model of which has some conserved quantum number. I mean, the truth is that we don't even understand why we have survived from the Big Bang. By any right, we should have wiped each other out. I mean, matter and antimatter should have annihilated. There should be nothing left, right? If we did not exist, it would be very hard for me to publish a paper saying, well, what about violating baryon number and violating charge and CP and having a microscopic arrow of time? And, if I do all this, then maybe I can create a baryon asymmetry. People would laugh at me. They would say it is too contrived. But we seriously entertain all those ideas because we are here to show that we are very contrived. We are very unnatural.
What I was saying, Subir, is that dark matter need not be massive. There is dark matter, but it can be massless. And classical condensates of these dark photons can also play the role of effective model.
I fully understand. So that idea would be interesting if you can propose an experimental test of that idea. Can we detect these dark photons in the laboratory? Actually, a lot of experiments are being done today looking for dark photons which carry a milli charge because of mixing between our photon and the photon in a hidden sector. So this is like a different tag, but that has a easy signature. You look for milli charge particles, for example, right? So if you could propose or correct your proposal to the program that is ongoing to look for particles like that, then that would certainly make it extremely interesting. Believe me, there's nothing experimentalists like more than to shoot down some interesting new idea. I can ask Ashutosh.
Sure, thank you. Anastasia, back to you. You have more to say.
Just one kind of comment on this. So we talked about like different challenges for cold dark matter, but you think that you can kind of try to resolve some of them. But what about dynamical friction test?
I'm not talking about dark matter.
No, I know, but now.
Oh, you're asking my view of dark matter. Yes, so the dynamical friction is indeed an important consideration. By the way, the person in the next office of mine is James Binney, who is a so I'm familiar with classical dynamics. Many of my collaborators here work on galactic dynamics, and what I have understood from them is that the real revolution in the subject, which is of course a very old subject, has been the arrival of data, in this case from the Gaia satellite. And in fact, the whole landscape of the field is now being transformed because of that experimental development. So whether those arguments about dynamical friction, which believe me, I'm old enough to remember when the same argument was used both forward and backward to argue for dark matter and to argue against it, right? So you, at one point, the argument was that spiral galaxies should have all formed bars, if they were dominated by dark matter. And then at some time later, the argument was reversed to say, well, they haven't formed bars, therefore there is no dark matter. And you really need a better formulation of the problem, that is to say, much more quantitatively, much more precise, and much better data in order to resolve those issues. But if you look in the literature, these arguments have been around for the last 50 years that I've been actually studying the subject. And especially about MOND, I've been fascinated by by Milgram's observation for many, many years. And as I said, I ask students to keep an open mind about dark matter until we actually find a non-gravitational interaction, right? But meanwhile, I think it is valid to pursue every means experimentally possible to look for both dark matter and for deviations from Einsteinian gravity. Both are well motivated, right? It's not a matter of one or the other. We have to know observationally what is possible and what is doable. That's the point. Nobody knows the answer, right?
Thank you so much. And if it's okay, like I would send you some papers from the recent papers on dynamical friction.
Sure.
Or probably you saw them. They're from 2-3 years ago with the new observations, and I think that they look really kind of hardcore kind of challenge to call dark matter. So,
as I said, I'm not really an expert on galactic dynamics, but I know some experts, so I would be very happy to discuss with them.
Thank you so much. Thank you.
Yeah.
Thank you. Subir, I would like to read out 2 comments, and then after that, Indranil has several things to say. There's a comment from Karthik saying that another issue with Daisy's 3.9 sigma claim about W and equation of state was that their peculiar choice of priors while performing Bayesian analysis. This subsequently leads to a strange...
So he's referring to this observation by Andrew Little and Marina. But this was actually something that was well known, that the way that you parameterize this equation of state, W, with a dependence on redshift. Now, this was a purely pragmatic choice, this so-called Linder and who was the other guy? Anyway, this parameter, there's no reason, no physical reason why W should be parameterized as a function of redshift, because if W deviates from -1, that means that it's not Lorentz invariant. Okay, only a Lorentz invariant observer can, well, W of -1 is invariant for all observers. If it is different from -1, then different observers will see it differently. In other words, dark energy should then have space-time variations, okay? Not variations in Z. That is simply because the equation for luminosity distance, the integral, is over Z. So if you put in a dependence on Z in that integral, then you can integrate it. It's just for calculational convenience. But that introduces some biases in how you analyze the data. And in fact, what Cortes and Little and others before them, for that matter, had pointed out, including, I think, Linder himself, is that you can have a bias that drives you to a particular value, even if that is not the actual value of the parameter in question. But my concern with the DAISY analysis was much deeper than that. I'm saying they start their massive paper with this beautiful new data set by assuming the Friedman-Lemaitre-Robertson-Walker metric, which was formulated 100 years ago. You would think that a modern experiment with modern data which has the ability to itself check that assumption, should do so before they make that assumption.
Yeah, just a related question. Would the Big Bang nucleosynthesis abundance calculations, which match well with data, would they get seriously affected if homogeneity isotropy assumptions are dropped?
Indeed, that is something that I do work on, and nucleosynthesis, as in formulated in the usual FAW model, is in reasonable agreement with data. I mean, you always get the helium abundance more or less right anyway. This goes back to the work of Alpher and Herman back in the 1960s. But the deuterium abundance is more non-trivial. It depends on the expansion rate. More on the baryon density rather than the expansion rate. And we do have a problem with the lithium abundance, which could be astrophysical in origin. So I say that to indicate that nucleosynthesis is a success. It allows us to determine the expansion rate of the universe at a redshift of around 10 to the 12 to within about 10% in principle. But that is something that is not written in stone. Right. I mean, I actually write the particle data group review on nucleosynthesis, look at the data every year. And whereas inhomogeneous nucleosynthesis has been studied, it has not been studied in as much detail as some other issues have been, simply because there has been no reason for people to do it. And the simple story works. But having said that, in general, the anisotropy I was talking about is not something that has to come from the early universe. The early universe could well be isotropic and homogeneous. And this is something that could have developed at very late times, around when structure began to form, right? Which was at a redshift of few. In fact, most of the structure formation is happening around redshift of 1. That is exactly when you start inferring the presence of dark energy. People have noticed this. Maybe it's not a coincidence. Maybe what we are seeing on the sky is essentially the effect of the universe turning inhomogeneous because of structure formation and the concomitant breakdown of the underlying assumptions that we made. Because apart from that, as you know, as a relativist, the usual Bianchi universes, which have torsion, shear, etc., they all decay extremely rapidly with redshift. So if they're important today, they would have been even more important in the past.
Yes.
Right. And then it would be very hard to understand why the microwave background looks so nice and smooth, why nucleosynthesis seems to work with the usual assumptions as well as it does, right? Yeah. So I think that on the whole, in the time, in research, you always have to choose some priorities. I'm not going to think about this as an early universe effect, because that makes the problem far too complicated. I think it is much more likely that the effects that we are seeing have to do with the late universe. But it is precisely in the late universe that we are inferring a value of lambda of order h naught square.
Yes.
Right. Yes. And that is what I really, Weinberg called it the bone in our throat, the cosmological constant problem. Right? It's hard enough to accept that we don't really understand why vacuum energy does not gravitate, but then to be told on the basis of astronomical data that there is a lambda of order 10 to the minus 42 GeV, that is even more unacceptable.
Yeah, right? In my view, the theory of lambda is very poorly understood. Whatever work I do suggests that the cosmological constant is actually 0, and the effect that we are seeing in cosmology has to do with something else.
Well, that would be consistent with the line that is saying that the effects that you're seeing are that something else.
Yes.
I think has to do with the growth of inhomogeneity in the universe. Yes. Now, to quantify that, I'm afraid I think we first need more data, because we have just started getting data. It is a myth that there is a huge avalanche of data in cosmology. When you actually start looking, you find there are only 1 million quasars. There are only a couple of thousand supernovae. They are very limited numbers. But the good bit is that the data is coming, and coming very soon. Okay, within the very near future, within the next 5 years, next 10 years, not 30 years from now.
Great.
So that is something I'm looking forward to.
Thank you. Bernd, please go ahead.
Thank you very much. I have a question concerning vacuum energy or your presentation of lambda. I would guess that you also agree with Tejinder and say that it's not a cosmological constant. Is this correct?
I'm saying that I don't see any evidence in the data for a cosmological constant because the inference was based on observing acceleration of the Hubble expansion rate. If it was due to lambda, it would have to be isotropic. Okay, that's the property of lambda. But what we are seeing on the sky is not isotropic, therefore it cannot be due to lambda.
Okay,
that is a purely empirical observational argument.
I see. Okay.
Apart from that, putting my theoretical hat on, I also don't think it can be due to lambda, because this lambda would then have to be fine-tuned to a value which is, as you know very well, many orders of magnitude below any reasonable scale.
120.
But that is, I think that is a weaker argument, because we don't have any understanding of lambda theoretically anyway. So to have a prejudice based on that is perhaps less defensible. But we all have prejudices. I just can't accept that there could be anything as ugly as that.
I see. But actually, we would need a theory of quantum gravity to calculate lambda.
Well, that is in fact my main grudge against the current theories of quantum gravity, such as they are, is that none of them have been able to address the cosmological constant problem.
Okay.
It's too hard a problem. I mean, I hasten to add that much smarter people than me have attempted it and not succeeded in solving it. So I can excuse myself for not having any original thoughts in the matter.
Okay, thank you very much. Thank you for the nice talk.
Thank you very much.
Another comment which I related to Mach's principle from Claudio Paganini.
Oh, yes.
With regard to Mach's principle, it is interesting to note that the theory of causal fermion systems is purely relational and hence Machian at heart. So I thought for completeness, I should read that out.
Frankly, sorry, I don't know what that theory is, but I will have a look at it. Causal
If you are
fermion
there,
system.
please, if you want to say something. Yeah, I'm not sure Claudio's there.
Okay.
Yeah, I'm here, but it was more sort of a comment. That's something. So basically, the theory is like all there is the correlations between the fundamental degrees of freedom that exist in the physical system, and so the theory really is fully relational. So that would point towards a Machian picture of the universe. But on an effective scale, I'm not sure whether this has any implications, like on a macroscopic scale, as in cosmology. So,
can I ask, by Machian, you mean the original Machian idea that inertia is a consequence of the distant distribution of matter?
Well, I mean, this is so it depends which. It's a very good question. I found about 20 different incarnations of Mach's principle.
Yes, that's why I'm asking which one you mean. Yes.
So I'm not 100% sure which incarnations it all satisfies. So. This is something I've just recently sort of like got interested in, but like certainly it's like all you have on the most fundamental level is like you have the Hilbert space given by like your gravitation, your fundamental degrees of freedom, and all the theory determines is the correlations between all these states that you have. And like the states give you the space-time, and like these correlations give you the space-time structure and all of it. So yeah, on the fundamental level, you only have correlations, and that is some incarnation of Mach's principle it fulfills. I'm not quite sure which all two. So yeah.
Okay. Thank you.
Thank you, Indranil. You had many comments. Would you like to say something?
No, I think my comments are just pointing out some links. I mean, for example, should we mention some of the recent problems for MOND, and I have a link which gives some more information about that.
Okay, great. Thank you. Anyone else in the comment field? If you wrote a comment and I missed out, if you want to say it out, please. Okay, then over to Jitu, your next question.
Professor Subi, you mentioned the scattering of a result in particle physics, which says the scattering should not be into the infinite future, otherwise the probability would be unconserved. So if we use some kind of symmetry in physics, like the time reversal symmetry, does it mean that universe had a beginning, or it didn't exist infinitely?
Well, the S matrix is usually formulated on Minkowski spacetime. You're talking about two particles in the lab coming in, hitting each other, going off. You measure the incoming particles, you measure the outgoing particles, you conserve probability. It is usually not discussed in the context of the global spacetime. The question that was raised when people first considered the possibility that we live in de Sitter spacetime is that, as you know, de Sitter doesn't have, there's no way to determine if the two particles who came in actually did go out, because there's no future infinity. So in principle, there is a problem. Whether there is a problem in practice or not is the issue that people are, in fact, currently engaged with. In other words, could this be a non-problem, in the sense that, after all, you could always have small patches of space-time that are doing whatever they're doing. Ultimately, if at some point I can construct some kind of a Cauchy surface and determine the outgoing probability, then I could conserve the S matrix and everything is fine, right? The question that Jia Dwali and also the other paper by Uguri and Obied addressed was whether that was specifically in the context.
Is it Hiroshi Oguri?
Yeah. So they were talking actually about the string theory landscape, which is a landscape of many vacuum states, each of which has a different cosmological constant, because these are all the combinatorial possibilities when you stabilize the so-called moduli, the scalar fields that determine the sizes and shapes of extra dimensions. So basically you have you have de Sitter vacua. So what they were arguing is that in fact, that is what is now being called the swampland these days, that actually you cannot have de Sitter space, right? De Sitter space is inconsistent with string theory. This is the claim that was made. It is not something that has been established. There is a lot of discussion and argument going on about it right now.
Professor Subir, are you meaning ADS-CFT, which says...
No, ADS is the natural home for Cyclic. I'm talking about DS, not ADS.
This discussion is going far afield.
Yes. Okay, so let me summarize by just, I think, answering what I think he's asking. The issue is whether, and this is nothing to do specifically with string theory. This is a general question that relativists have been concerned about for a long time. The question is de Sitter space somehow fundamentally unstable for some reason, right? Is it allowed by nature?
Yes, that question.
Yeah. So that is the question that we are that I just referred to some interesting work in that direction. If it turns out that, say, de Sitter space is forbidden, just like, I don't know, naked singularities are forbidden or something, that might actually change the mindset of people about invoking lambda in the context of trying to explain the inference of cosmic acceleration, for example. So okay. I just said
Thank
that.
You. Thank you, Subir.
Yeah.
Could you kindly, Subir, stop sharing slides so that we can see us on the video?
Okay.
So perhaps it's now we finished 2 hours. Maybe tiring you now, Sunil.
Okay.
Sorry, Subir. So, Bunt, something pressing, or you could write to Subir?
Yes. Only something concerning de Sitter space. Wigner and one of his students, Phillips, already proved in 1968 that you cannot define a Hamiltonian on de Sitter space which is bounded from below. So you don't have a positive energy theorem for de Sitter spaces.
Right.
Space-time, so to be precise.
So I see. This was. Do you know the name of the author? It's a student of Wigner.
It was Eugene Wigner and Theo Phillips.
I see. Okay, Philip. I'll certainly look at that. That sounds very interesting. Thank you.
Yeah, I can send you the paper if you want.
Yeah, that'll be great, actually. Thanks.
Okay.
Thanks.
That's all.
Bernd, yeah. Any more comments or questions, please?
Yes, you're right. We have gone past 2 hours.
Yeah. Thanks so much, Subir. It was wonderful.
Well, thank you all for staying. I'm impressed that you have the energy to stick at it so long. Okay.
We love the discussion as much as the talk, because anything that's lingering at the back of the mind we put to the speaker. Yes.
Well, absolutely. And I would be happy to have any email queries later if people think of something later.
Great.
Okay. Thank you.
Right, so maybe it's time to start winding up. So
yes.
we have a talk 2 weeks from now, Jochen Sangolis. So we'll see you on July 19th.
Okay.
And it's time to, I guess, there's some comment. Claudio, thanks you for the talk. So I take your leave and say goodbye to all of you.
Okay.
So maybe first you go log out, then I log out.
Okay. Thanks for organizing this thing. Bye-bye.
Bye.